Hi everyone, we are going to talk about the second part of Chapter 6. This is covering sections 6.7 and 6.8. So we're kind of taking a drastic turn from where the first half was. The first half was an overview of enthalpy and kinetics. And in this portion, we're going to start talking about how reactions happen. And for the most part, what we're looking at are the patterns that we see reoccurring throughout the remainder of the chapters. Most of the reactions that we talk about are based on electrostatic attractions. So this is an attraction between anything positive and anything negative. And we use the word positive and negative kind of lightly. On the next couple slides, we'll add some information to that. But here we have just kind of our basic information, and we can see that our negative charge we know is attracted to our positive charge. That's our electrostatic attraction. And following that color coding here, we can also label a negative charge as something that is electron rich, and something that is positively charged is electron deficient. Something that is electron rich, we can also call it nucleophilic. So we know that that suffix philic means love or like. So if it's nucleophilic, that means that it loves the nucleus or loves the protons within that nucleus. So something that's electron rich is attracted to protons, which means that it's nucleophilic. And then the same thing is true for our positively charged species. They are going to be electrophilic. So the philic part is telling us that they love electrons. So if they're positively charged, they're going to be attracted to electrons. So let's see where those are going to occur. We're going to start with the nucleophile. And we can call an atom a nucleophile, or we can refer to it as a nucleophilic center. Nucleophiles are going to be attracted to a nucleus, or specifically the protons. They are electron rich. They can donate electrons, and so because they're donating electrons, they are technically classified as a Lewis base. We don't generally use that label, but they are falling under the same category. So our examples down here, we have a carbon that is partially negative because it's attached to something that is less electronegative than it. We have a full negative charge on our oxygen. We have a lone pair on our oxygen, and then we have a pi bond. So all of these are examples of electron-rich areas, which means they are all nucleophiles. In our electrophile category, these are electron deficient, which means they can accept a pair of electrons, and again, that puts them into the Lewis acid category. Our examples for our electrophiles or our electrophilic centers are atoms that are partially positive, have a full positive charge like our carbocation here, or something with an empty p orbital. Now, our empty p orbital could be from this carbocation. Another example is something like a boron atom. When boron forms bonds, it only likes to have 3 bonds. So it's going to have an unfilled octet. Here's our little summary table, and this is straight out of your book, so you can reference it, but it's showing us the examples of nucleophiles and electrophiles. When we have those partial positive and partial negative charges, those are the inductive effects. So we've seen that word show up a couple times. Really, it's just referring to the difference in electronegativity. And in this case, it's causing us to have those partial charges. So let's do problem or two. So in our question here, we are asked to identify all of the nucleophilic and electrophilic centers on the molecules below. Now, one important thing is that there can be more than one nucleophilic center or more than one electrophilic center on an individual molecule. So if we start with this one here, we have a ketone, we have an alkene, and if we start by looking for our electrophiles, so I'm going to circle our electrophiles in blue and our nucleophiles in red. If we start with our electrophiles, we know that we're looking for something that's positive, partially positive, or an unfilled octet. So within that structure there are not any unfilled octets, but we do have a partial positive carbon because it's bonded to that electronegative oxygen. So that's our inductive effect. And then if we look for our nucleophilic centers, we're going to have quite a few in this structure. The first one is our pi bond over there. So that was one of our direct categories. The next one is the other pi bond. The lone pair on that oxygen counts as a nucleophile. And then the oxygen itself, because it's more electronegative than that carbon. So just within this structure, we have 4 nucleophilic centers. So moving on to our magnesium bromide compound here. So we have this carbon magnesium bond, and carbon is more electronegative than our metal magnesium. So because of that, carbon is going to be partially negative. It's going to be our nucleophile, making magnesium partially positive, our electrophile. Down here we have a nitrogen with a negative charge and 2 lone pairs. So because of that negative charge, our nitrogen will be a nucleophile, and our nitrogen has a lone pair. So it's going to fall into that nucleophilic category for 2 reasons. And then our carbon that's bonded to it is partially positive because of that inductive effect. And then lastly over here, we have aluminum. Now we'll see aluminum pop up a few times throughout the semester as a catalyst. Oh, I skipped one. Let's go back over here. So I have my hydrogen circled here in green. I have it circled in a separate color. It is going to be partially positive because it's bonded to that nitrogen, but it's not an electrophile. And the reason why is because when our hydrogens are partially positive, we give them a specific label as being acidic. So I wanted to address that before we moved on. All right, back to our aluminum. So with this aluminum structure, because it has that unfilled octet, it has 3 bonds, 6 electrons surrounding it, it doesn't have a full octet, that's going to make it an electrophilic center. And that's one of the reasons that we'll end up using it as a catalyst later on. So now that we can identify our nucleophiles and our electrophiles within a structure, we're going to use that information to see how 2 compounds or 2 species can come together and react. And we're going to specifically look at mechanisms. A mechanism shows us how a reaction is happening. It's showing us how the electrons are moving around throughout that reaction. And we show that by using curved arrows. These are also referred to as electron pushing arrows, and they're showing bonds breaking and bonds forming. The example that's down here is how we've seen this before. We have looked at mechanisms and curved arrows for acid-base reactions. So the arrow going from our nitrogen to our hydrogen is showing that bond forming, that nitrogen-hydrogen bond forming. And then the arrow going from the bond to the oxygen is showing the oxygen-hydrogen bond breaking and the formation of that new lone pair we can see right there in red. There are 4 main categories for mechanisms. We're going to go through each of those 4. So our first one is called a nucleophilic attack. And within a nucleophilic attack, we're going to have a nucleophile and an electrophile, and our curved arrow will start at our nucleophile and end at our electrophile. Now, normally, this is going to be one arrow showing that bond forming. If there needs to be another arrow, it will be because of resonance or electron flow. So the tail of the arrow, the start of the arrow, is at the nucleophile at that negative charge or partial charge, and then the head of the arrow is at that positive charge. Our second category is the loss of a leaving group. And again, there's one arrow that shows the loss of that leaving group, but there might be other arrows that are needed for resonance or electron flow. So here's our loss of a leaving group arrow. We're going from the bond onto the leaving group, and our arrow is showing that bond breaking, and the electrons are going onto the bromine as a lone pair. And in this case, our carbon ends up with that positive charge as a result. The third category are proton transfers. This is also in the acid-base category, and it usually requires two arrows because we have to move the hydrogen from whatever it was attached to the new thing. So we have to show a bond forming and a bond breaking. And we can divide this up into protonation, so adding a hydrogen or a proton. So here we have an oxygen with a lone pair, so that is our nucleophile, and we're going towards that hydrogen, and hydrogen can't have two bonds, so we're breaking the second bond right here with that arrow. So this is technically falls under that nucleophilic attack category, but because our electrophile is a hydrogen, it goes into a more specific category. And then our other one is deprotonation. So essentially it's the opposite of what we just did. We're going to remove this hydrogen. So here is our base that's going to remove our hydrogen. So we're forming a new bond from the lone pair to the hydrogen, and then we have to break the pre-existing bond. We're going with an arrow from the bond onto the oxygen to form that lone pair. And then our fourth category is a little bit different than the other ones. These are rearrangements. And what we're looking at here are carbocations. And we've talked about carbocations before, but we haven't necessarily talked about their stability. So this is showing us the trend of carbocation stabilities. Notice that a methyl carbocation is the least stable, and a tertiary carbocation is the most stable. So we're categorizing them by how many other carbons are attached to them. So a primary carbocation is bonded to one carbon, secondary is bonded to two, tertiary is bonded to three. The reason for that increase in stability is because of hyperconjugation. So we've used that word a couple times before. Really, it just means that when there's extra bonded electrons available, they can overlap into that empty p orbital that our carbocation would have. So when we have more things bonded to our carbon, there's more electrons that can do that overlapping. Now, because carbocations are not stable, making them as stable as possible is going to be what's important. So within our carbocation family, it can go through a rearrangement to become more stable. And there's two ways that that can happen. We can do a hydride shift, or we can do a methyl shift. And specifically, we call it a hydride shift. The "ide" means negative charge, so a hydride is a negatively charged hydrogen. And we can see that in the mechanism because our arrow is starting at the electrons of that bond, so the hydrogen is taking its electrons with it and going towards that positive charge, going towards that carbocation. So going right here. And when that hydrogen shifts over, we now have a tertiary carbocation, and it started as a secondary carbocation, which is an important thing to point out because this carbocation shift is only going to occur if it becomes more stable. Now, a methyl can also shift. This is going to be less common. If a hydrogen is available for shifting, that's going to occur before a methyl. And we can't shift anything larger than a methyl. So with our methyl shift, same idea. We're going from the bond of that methyl towards that carbocation. And in this case, again, we're starting with a secondary carbocation. And after that methyl shifts over, we end up with a tertiary carbocation. So it will only happen if it's more stable. It will only happen with hydrogens and methyls, hydrogen being the preferred method if available. And it will only happen between adjacent carbons, which is why they're called 1,2 hydride shift and 1,2 methyl shift. It's referring to how close they are together. They don't necessarily have to be on the first and second carbon of our chain. So in our next video, we'll do some practice problems with with these mechanisms and kind of putting them together in multiple steps. For now, this is an introduction of our 4 types, and then we'll start using them in our next video.